Welcome. This is Dr. Crown. I'd like to give you some assistance with homework 1, problem 1. An ideal gas, oxygen, at P1 and T1 is compressed in a piston cylinder assembly, first isothermally to P2 and then isentropically to T3. Do not assume that the specific heats are constant. Determine the following given the properties listed below. Here I have the mass given, the temperature at state 1, the pressure at state 1, pressure at state 2, and temperature at state 3. I'd like to begin by going over the equation sheet that I've developed for Thermal 1 about 20 years ago and still find extremely useful. Let me pull that up. You probably want to print this out and make sure you're familiar with everything on the sheet, because this is what I expect you to know from Thermal 1 and be able to be familiar with all these equations, if not have them memorized. The first equation that I've highlighted here is the first law for a closed system or a control mass, where the mass is constant, which would be the case for this problem, where we have a piston cylinder assembly and the mass of oxygen is trapped in the piston cylinder assembly, so there's no mass going in and out. We will allow the control volume, or the volume inside the piston, to change as we push the piston face. So the piston face represents one of our system boundaries. The equation is Q minus W equals delta E. Delta E can be expressed as delta U plus delta KE plus delta PE. In this particular problem, we're assuming that the change in kinetic and the change in potential is 0. So we're neglecting any possible changes there, or we can make a safe assumption if the piston's lying on its side that the elevation's not changing and it's the piston's moving slowly, so we're not imparting kinetic energy to the center of mass. Also, we'll be looking at the equation for boundary work. Since we have a piston acting at the boundary, we'll be doing some work on the piston as we compress it, or on the gas as we compress it. And the boundary work is calculated the integral PdV, where P is pressure and V is the volume of the gas, in this case oxygen. Going down a little further, we have some expressions for working with ideal gases. On the equation itself, it just has one form of the ideal gas equation that I have highlighted there. P lowercase v equals RT. That's the pressure times the specific volume equals the gas constant, in this case, the one for oxygen, times temperature. And always express temperature in absolute, either Kelvin or Rankine. Right below that, I have another equation for the ideal gas law. P capital V equals N RT. And there's a bar over R, so I'll usually say R bar. That's the universal gas constant. The value is 8.314 kilojoule per kilomole K in SI. And you can find that on the conversions factor page. In this case, the capital V represents volume, the volume of the piston cylinder assembly, the volume of the gas. We can find delta U. In this case, that's specific internal energy, from finding the specific internal energy at the two end states. So the change is just U2 minus U1. We can find the total change in internal energy rather than specific by either multiplying delta U, little delta U, by M, the mass, or U bar, delta U bar, times N. So in this case, this equation here, I'm going to highlight, is the one we'll be using in this homework problem. So the change in internal energy equals N times U bar at state 2 minus U bar at state 1. And those values we can find in the ideal gas tables. Similarly, we can find the change in specific entropy, delta S bar, and it's equal to S2 naught bar minus S1 naught bar minus R bar times natural log of P2 over P1. And you'll notice the one I have highlighted there is per unit mole. So this, or per unit mass rather, this one is per unit mole. And since we're calculating the moles of oxygen and S bar is given in the tables, this would be the easiest one to use. All right, let's begin with determining the moles of oxygen. So one thing we need to know is that molar mass and molecular weight is simply m over n. And we can go to table A1. So oxygen is what we have for gas, and the molecular weight or molar mass is 32 kilogram per kilomole. We know that m over n is 32 kilograms, and we're given m. So m is 0.3 kilograms. So we simply just solve for n. N equals m over the molar mass. So we have 0.3 kilograms divided by 32 kilogram per kilomole. And if we do things right, the units cancel, and we end up with 0.009375. And if we go to our homework system, we have a place to enter that value. 0.009375. And if you watch the introduction video, you saw how that was entered and calculated. All right, let's move on. Determine the change in internal energy from state 1 to state 2. We can write out the equation for internal energy, and we'll do it per mole. So we have N times U2 bar at T2 minus U1 bar here. All right, now, if we're thinking ahead, we can save ourselves some time, but let's go ahead and look up U bar at T1. So we'll go back to our tables here. We'll have to go quite a ways down. And we're looking for table A23. And we find oxygen. And we see U bar here. And our temperature T1 is 550 degrees K, or 500 Kelvin, 50 Kelvin. And we find that here. And we go across and find U bar for oxygen. And we find that it is 11,765. And we can find the units there. For U, we have units are kilojoule per kilomole. And note it's per kilomole, so we would have N as 0.009375 kilomole. So we're going to end up with a delta U in kilojoules when we multiply through the units of the kilomoles will cancel. Now we still need U2. So we have to find T2. So let's go back up to the problem statement. T1 is 550, but we're told that this first process is an isothermal process. So we've got an isothermal process. Which simply just means that T equals a constant for this process. That means at the start of the process, it's going to continue throughout the whole process, the temperature not changing, and at the end of the process, it's at T2, so T2 must equal T1. In fact, the temperature never changes during the process. So T2 equals 550. Okay. So when we go to look up in the tables, U bar at T2, we'll find out that U2, U bar 2, which is at T equals 550, same as U1, it's going to equal 11,765 kilojoule per kilomole. So we've wasted a lot of time. we have a number minus the same number times 0.009375. And so we know that the second term here will equal 0. So 0 times anything is still 0. So the change in internal energy from state 1 to state 2 is 0 because the internal energy is only a function of temperature for an ideal gas, and the temperature has not changed. And maybe just to review that, if we went all the way back up to what we looked at before, that's why it's very important for us to remember that it's not highlighted anymore, I think it closed, but that the internal energy is only a function of temperature from the ideal gas tables. And just seeing that from the tables themselves, you can see that all we need to know is the temperature. We know the temperature, we can find the internal energy. We don't need to know the pressure. All right. Determine the work from state 1 to state 2. Let's use the first law of thermodynamics. Q, for closed system, minus W equals delta U. We know this is 0 from the previous problem. And now we're kind of stuck. We do know here that Q must equal W for this process. So Q from 1, 2 has to equal work, process 1, 2. But we don't know the work yet at this point. So what we can do is use another equation, which is the boundary equation for boundary work. So that's the only work we have in this problem. And for boundary work, this is problem 1, 2, it equals the integral of P dV. And we can express P using the ideal gas law as N R bar T over V. So if we substitute that in, we have the integral of N R bar T over V dV. And the moles of oxygen isn't changing in this process. The gas constant's not changing. The temperature is not changing. It's an isothermal process. So we have 3 constants that we can take out. N R bar T integral 1 over V dV. And we can do the integral 1 over V dV. That's just the natural log. And we have limits of the volume at state 1, state 2. So we end up with the boundary work from 1 to 2, which is the work. Same thing, it's the only work term we have, equals N R bar T natural log of V2 over V1 when we evaluate it at its limit. Now we can write P2 is equal to N R bar T over V2 and divide by our definition of P1 on both sides. So P1 on the left side there in the denominator, and P1, though written using the ideal gas law, N R bar T over V1. And why am I not using T2 or T1? Well, it's not changing in the process. So the N cancels, the N doesn't change, R bar doesn't change, T doesn't change. And so I'm left with V1 over V2 is equivalent to P2 over P1. So I can make a substitution here and replace V2 over V1 with P1 over P2. And I get N R bar T natural log of P1 over P2. P1, I believe, is 1.5 bar and P2, 4.5 bar. So finally, I can have the work 1 to 2 equals 0.009375 kilomole times R bar 8.314 kilojoule per kilomole Kelvin times 550 K times natural log of 1.5 bar over 4.5 bar. And we work that all out on our calculator, and we end up with negative 47.096. Kilojoules, although the answer sheet, you don't need to enter the units since they're specified in the problem. All right, moving on to problem 4. What is the heat transfer? Well, from problem 3, we learned that the heat transfer is equal to the work. So Q12 just equals work 12. So it's also minus 47.096 kilojoules. Part 5. Determine the change in entropy from state 1 to state 2. So this equation, I want capital S, so N times delta S bar. And we can write S delta S bar as S2 naught bar minus S1 naught bar minus R bar natural log of P2 over P1. And all that multiplied by N will give us the change in entropy, not per unit mole. So where do we find these values for S2 naught and S1 naught? From the tables, so from the ideal gas tables. Now when we go there, this will be S1 naught bar at T1, and this will be S2 naught bar at T2. Now when we look up those values, which we can go to the tables here, E23, it's ways down here. And we find out that at 550, it's 223.576. And when we look it up again at 550, it's still 223.576. So S naught at state 2 and S naught at state 3 is the same. So those terms will cancel. However, we still have a term that won't cancel. So this term cancels. That term is 0. The difference is 0. So they're not both 0. It's just 223 minus 223. So we still have equals, so we'll put the minus out front, N times R bar natural log of P2 over P1. And again, this is 0.009375 times 8.314 times the natural log of, in this case, P2. So I'm going to leave the units off this time. And we end up with negative 0.08563. Don't forget that we do have a negative sign there. That's where this came from. All right, moving on to part 6. We're going to use the same equation, but note that for our second process, it's isentropic. Isentropic means the entropy doesn't change. So if we write this equation, so delta S equals 0, which means that N delta S bar equals 0, and which means then that delta S bar is 0. So we have that this expression up above, do it for, so we have state 3, state 2, so it's going to be P3 over P2. So don't memorize this as a new equation. This is just the same one, but we use the appropriate subscripts for our process. So now we're looking at the process from state 2 to state 3, second process, which is isentropic. So if it's isentropic, we mean the entropy doesn't change. So isentropic means delta S equals 0. All right, now we're looking for the pressure. So we need to find S bar at T3. And S bar at T2. Now these won't be the same because at T2, we found it was 223 point something. And we'll get that point something because it will make a difference. But T3 is 650. So if we go to our tables, going back to the booklet, down to 650, which is our temperature at state 3, and we find out it's 228.932. And again, this is kilojoule per kilomole. Okay. So now I have those values. I have that R bar is 8.314. And so I can solve for P3. And probably the easiest way is to divide both sides of the equation by R bar, and then take the inverse log. And then I'll have P3 over P2, and then multiply both sides by P2. So I end up with P3 equals P2 e to the power S3 naught bar minus S2 naught bar divided by R bar. And I get bunch of those values in 228.932 minus 223.576 divided by 8.314. Take the inverse log of that and multiply it by P1, or rather P2, which I believe is 4.5. And I end up with P3 equals 8.5702. So again, we're using the same equation twice. In one case, we solved for delta S. In the other case, from the wording of the problem, the processes, we determined delta S was 0. So now we can solve for some other unknown. In this case, it was P3. Determine the change in internal energy from state 2 to state 3. So from state 2 to state 3 is our isentropic process. So we know the temperatures, so we can find the change in internal energy. So we have delta U equals N U3 bar, which is function of T3, minus U1 or U2 bar, rather, which is function of T2. So we simply go to the tables and we look up those values for oxygen. So at 650, we find out that U is 14,140. And this is kilojoule per kilo. And then we go look at 550. And at 550, we find for oxygen, U is 11,765. 11,765. So 14,140 minus 11,765 times, again, 0.009 goes 375. That's kilomole. So I'll end up with kilojoules for an answer. And I believe I get 22.27 kilojoules. Determine the heat transfer from state 2 to 3. Well, we're going to assume that all these processes are internally reversible. So isentropic generally means reversible, at least internally reversible, and adiabatic. So if we know it's isentropic And we know it's internally reversible, and it must be adiabatic. So adiabatic just simply means Q 2 to 3 is equal to 0. So there's no heat transfer for this process. So the answer here is 0. Determine the work from state 2 to 3. Well, now that we know that Q23 is 0, we can use the first law. And we already have an answer for U23. We know this is 0. So work 23 just equals the negative of U23. All right, then finally, does the gas heat, cool, or not impact the surroundings in the process from state 1 to state 2? That's our isothermal process. So we were compressing a gas. Normally, the gas would heat up if we compress it, but it didn't. It stayed the same temperature. How is that possible? Well, we must have been cooling the cylinder while we compressed the gas. And so what happened when we cooled the cylinder, we heated the surroundings. So we have our piston cylinder assembly. This piston's moving up. There's our oxygen. So we've been applying. So this is our system. This is our system boundary. And we've been applying these laws of thermodynamics to the system boundary. In this case, we had Q12. We had work being done here. This is work 1, 2. And then we had delta U 1, 2 happening. So we're able to say, if we know the work and we know the heat transfer, then we can determine delta U. We can have any two knowns and we can find the third. So that's the power of thermodynamics. You can isolate a system from the surroundings. So the surroundings is everything outside that what I've labeled the system. And the interaction between the systems and the surroundings will affect the properties of the system. So that's really all that thermodynamics is about, is isolating something that we want to study and then looking at the interactions with the environment. And then we can keep going in greater and greater detail. So if we have a very complex system, lots of things can be happening inside there, and we don't really want to look at those. We just want to simplify. So we draw a big box around everything, and we look at the interactions with the surroundings. And then once we get an understanding for, okay, what's going on across that boundary, we can narrow in and look at smaller components. And so we'll be looking at the start of this course, steam power plants. And we can draw a big box around the entire steam power plant and determine what the efficiency is for that. And then we can start looking at all the different components, all the pieces of equipment in that, and then start understanding more and more details the more we go into smaller and smaller system boundaries. We can look at what's happening right around a turbine blade, or we can look at the entire turbine, or we can look at everything within these processes to greater and greater detail as necessary.